So thank you very much. Thank you, Steinar, for that wonderful introduction, and welcome to IAMG 2023. And also thank you, Peter, as our current president, and for the invitation and welcome. I'm really delighted and honoured to be the IAMG Distinguished Lecturer. And my first slide is unashamedly about the IAMG. And I suppose the first IAMG conference that I attended was in Portsmouth in 2003. So that's 20 years ago. So very nicely put, Steinar. I am one of those who have attended more IAMG conferences. Not by far, people here have attended a lot more than me, but I really encourage all of the PhD students, the early career researchers who are here, and I really hope that the IAMG will become, as it has done for me, a nurturing community and family. So do please take up the opportunity to really network with those around you. So I'm honoured to be the IAMG Distinguished Lecturer. And at that first conference, I then did publish in mathematical geoscience from that conference. So as a PhD student or an early career researcher, yes, you can submit papers and publish in IAMG journals. Now, I come from, and I suppose the last thing I should say just on this slide there is, I really want to also emphasise the Encyclopedia of Mathematical Geoscience, which has just been published. Thank you to all of the authors who have participated in this. And I think it's really a showcase and an accolade for Digga Saya, for Chiming Cheng, for Fritz Attenberg, and I'm honoured to be one of the co-authors on that publication. So again, it's a testimony to the community of the IAMG. Now, the IAMG, as we all know, advances mathematics, statistics, geoinformatics, machine learning, all of the different types of spatial data analysis techniques in the geosciences. And I come from the geology end. So I am a geologist and then a mathematical geoscientist. And that means that I have been involved in quite a number of different fields, from restoration of natural heritage, like the wonderful cathedral that we saw yesterday, right through to natural resources, whether it's estimation or monitoring or conservation of those, right through to renewable energy, and also more and more in terms of health in the environment, and that includes pollution, and also maybe what you may not consider mathematical geoscience to be involved in, but geoforensics. It has also brought me into contact with so many partners and different organisations, international organisations as well in these fields. And I must credit the PhD students, the postdocs, my colleagues who have also been involved with me in bringing mathematical geoscience in all its different forms into these different fields. Now, I want to concentrate on two fields for this talk, and the first is health and the environment, and then also geoforensics. And if the little diagram that you can see just on the top right is really showing that even for forensics, something like mud, natural resources on your shoe, you can get that microstratigraphy. Therefore, the skills of a geoscientist and a mathematical geoscientist still apply. So for this talk, I want to touch on a number of different projects that I'm involved in at the moment. The first one is a European Horizon 2020 project, working with a number of different partners across Europe. The second one in health is a UK-funded project, which is looking at healthy ageing. So how does the environment that we live in affect how we age, and why do some people get more affected than others? And then the third one is the International Initiative for Forensic Geoscience, or geology. So let me start with forensic geoscience. And this might be new to you, but the initiative of forensic geoscience was started really by the JOSOC of London, but then also by the International Union of Geological Geosciences. It was started as an initiative of the IUGS in 2011. And the aim of it is to develop forensic geoscience internationally and promote its applications. And mathematical geoscience is part of that. So what does forensic geoscience mean? Well, it means a whole number of different things, but it's basically the application of geology to forensics. And that can be criminal investigations, it can be the search for the people who might have disappeared, or are missing, or are lost, humanitarian incidents, environmental crimes, wildlife biodiversity crimes, mineral substitution, conflict minerals, even geotechnics, geohazards, and those are only some of the applications. So it's a very wide-ranging area. But we like to break forensic geoscience down into 3 different areas. Really, the search, the scene, and then trace evidence. So 3 different scales. And if we start at the larger scale, the search, that can be global, it can be countrywide, it can be over an area, and it might be for a missing person, or it might be for missing humanitarian. And again, you can see the influence of geology, remote sensing, all of bringing together those different data layers to integrate and find particularly maybe a local area. The scene then brings it down to a little bit more of a narrower search, and then we're actually interested in one particular scene, one particular area. And the quote here from Hans Gross in 1893 as a magistrate, he recognised that dirt on shoes can often tell us more about where the wearer of those shoes have been than toilsome inquiries. And then Conan Doyle is one of the writers who picked this up in his character of Sherlock Holmes, and again linking mud between urban pavements to somebody's footwear. So that smaller area scale brings us right down to trace evidence then. And trace evidence, I think, is put very nicely in terms of the quote by Edmund Lockhart, and this is one of the key principles that we work by. Whenever 2 objects come into contact, there is always a transfer of material. Our technology might be only advancing at a certain rate, so we might not always be able to pick that up, but there's always been that transfer. And that's a really important thing that in forensic geoscience and mathematical geoscience, we can also use. So let me go into a little bit more detail about trace evidence. And you can see the nice slides, the nice pictures on the slides. Some of them you might recognize from CSI and other types of programs. So mud on shoes, if you're lucky enough to actually get something like a spade or a weapon like a knife, there might be some sort of natural material on it. It's not as frequent to get the vehicle. Sometimes people are becoming forensically more aware, so they take it through a car wash. But generally, the car wash doesn't get rid of some of the material around the hubcap. So you can always find that piece of forensic information. So geological trace evidence is a collection of soil, rock fragments, microfossils, or any man-made material that is still coming from our geological materials. So again, that includes glass, blocks, building blocks, concrete, tiles. And again, what we want to do is to see if there's any association between the samples taken, they might be from a victim, and then associate that with a suspect or a crime scene. We don't use the word match, and I think as statisticians and mathematicians, you'll appreciate that we can never say there's a 100% match. There's always an uncertainty. So we use the terms association. And again, this is based on Edmund Lockhart's principle, every contact leaves a trace. So I want to use a case study. There's no unpleasant scenes in this apart from, unfortunately, a body deposition site. But I want to use this and then bring in some mathematical geoscience. So this is the unfortunate case of the murder of a young woman. And the suspect was believed to have lured this poor woman, who was only 24 and quite a vulnerable young woman, into his home where he killed her. And then he discarded her remains, used an old duvet to just cover her, put her in a bin bag, and then dumped her remains in a car park, which was actually quite close to his flat. The blue bin bag was found containing her remains, and it had these particular dark and light stains. And you can just see the area where he deposited her body, and just some flowers left. So a particularly nasty just case. So in forensic evidence, believe it or not, from a very small trace of materials, we can actually get a lot of information. And ChemScan is one particular scanning electron microscope technique where we can get a lot of information from a small piece of trace evidence. Now, these photographs are not from our particular case, but it gives you an idea of the range of different types of natural minerals that we find, even in things like car mats and things like that. In ChemScan, we can scan a very small amount of material. We can get a spatial distribution, but we can also get a proportional distribution of materials in that sample. So if we look at the ChemScan results for this particular case, then they're presented to us as these. And this is quite an expensive technique, so you don't have too many samples that you run through this technique. But this is what they might look like, and this is the results for this particular case. So you can see that we have a range of different types of, compositions in themselves, if you like, and they're presented, and these are the sample numbers. And I should just acknowledge my colleague in forensic geoscience, Alistair Ruffle, in this case as well. And you can see the different amounts of these different types of materials in each of the samples. Some of the samples are taken at the body deposition site. Some of them are taken from the suspect's home. And what we want to do is find, is there any association between these? So if we see samples like this, I know several colleagues in the audience will be immediately going, we have an issue here. So we have a forensic compositional conundrum. We have samples that have been made to equal 100%, because if it's an unknown, just other is put in there. So they do equal 100%. If we're trying to find an association between our suspect's home and the body deposition site, then we need to compare these samples. But how do we know whether a 3% or a 3 parts per million, is it large or small? You might automatically think, well, that's very small. May not be that important. But compared with, say, 80% or 80 parts per million, yes, it might be small. But what about if it's compared with another sample that is 0.03? So it depends. It's relative. So how do we deal with relativity in these samples? So data can be reported in any different types of units, and I haven't shown any units on this slide on purpose. They can or cannot add up to 100. It doesn't matter, 100%, but they're still parts of a whole. So as one changes, as one proportion changes, then the others will automatically change. Now that's an issue because these are just samples that have collected in the ground. If another sample was taken, the same minerals might be in there, but the proportions might change. So how do we look at this without the issue of proportionality, of relativity coming into play and resulting in us potentially having a conclusion that then could be falsified in court? So we need to proceed with caution. Now, through the IAMG, a part of our mathematical geoscience community has developed, as you know, compositional data analysis. And we can apply this to any proportional or compositional data. And again, in this case, these forensic samples are proportional. So we need to apply some sort of compositional data analysis to them. So what we need to do is use our compositional data approach to open up these constrained data sets. Now, we do have some issues in using compositional with forensic data. The number of sample points is only about 7. Remember, it's expensive to run these through, but we have many, many components. In this case, we have 30 components, but we only have 7 samples. So that is an issue that still needs to be fully addressed within compositional data analysis. And certainly forensics is not the only area where this might be an issue. But it can be done. So let me introduce just another aspect of what we look at in forensic science, which is the idea of unique particles. When you see something that is particular or peculiar, then possibly we can use that. In this particular case, it was these metal curls that were found on the body deposition site in this duvet, but also at the suspect's home. So could we associate those? Would they be sufficient? Would that be robust enough to associate the suspect's home and the body deposition site? And again, these were found on the roof of the suspect's flat and on the steps leading up to the suspect's flat. So the traditional way to present the ChemScan results would be something like this. So you'd get a number of different graphs, you would show these proportions, and actually this is a very friendly and probably visually attractive way to present the results. In this case then we can actually highlight this ferric oxide material from these curls, metal curls, and we can actually associate the body deposition site or some of the samples from the body deposition site to some of the samples from the suspect's home. And actually this has been presented in court and was part of the evidence that resulted in a successful conviction. But is it robust enough? So if we apply compositional data analysis to it, and in this case it's a very simple approach of using the centered log ratio and principal component analysis, then we can see that we actually get a very clear association between these dark samples in the duvet, which are attributed to partly to these metal curls, and the suspect's flat. So the image that you saw before, which is very visual, nice representation, but this is a very clear, robust way. And again, I should acknowledge my colleague Eric Gronsky in this analysis. So, sounds good. We can say it's a robust analysis, and we're actually looking at a number of different cases in ChemScan analyses using a compositional approach at the minute. And we're not trying to overturn any cases. We just want for ourselves to be assured that they are robust. So actually, in this case, the tragic victim was called Shirley Finlay, and Henryk Gorski was convicted of her murder. These were not the only pieces of evidence leading to it. We had witnesses, we had fingerprints, but the metal curls, the geochemistry, all added to the overall case. He appealed, and he was unsuccessful in his appeal, so he is still in prison. The issue of using trace evidence in a compositional data analysis approach in forensic science has not been represented or presented in court. There's a number of different challenges. But we need to know that our samples and our analysis behind the scenes is robust, even if it's a very simple representation that is presented in court. So I want to move on now to the environment, to health and the environment. And it is a chilling fact that the World Health Organization, the WHO, attributes that 23% of all deaths can be attributed to the environment. I actually think that that's probably underestimation if you start to think about some of the associations or the links between the environment and different types of health, including healthy aging. But that amounts to 12.6 million deaths per year. It is a significant amount. So geoscience and health, and mathematical geoscience and health, is really important. And this links obviously a number of the Sustainable Development Goals. One of the projects that we are really sort of into past our first year in is a nature-based solutions project, Upsurge, which is a European-wide project. It is one of 3 that was funded in this call. We have a number of different cities across Europe that we're working with, including in Slovenia, in Hungary, in Poland, in the Netherlands, and in Northern Ireland, in Belfast. And these cities, as well as many other partners, but these cities have large demonstration sites, as we call them. So we're monitoring before, implementing some nature-based solutions, and then monitoring afterwards or during. And part of the issue that we're looking at is pollution. How do we alleviate pollution? What the impacts of pollution? One of the issues when you're looking at these environmental sort of sites is that, sometimes people think about community gardens growing in a soil, but they don't actually think about what's in the soil. So yes, we might want to grow urban crops, agriculture. In urban agriculture, we might want to embed some nature-based solutions. But what is this actually the plants going to take up from our soil? So the urban sites in particular, and this is the one in Belfast, which is located, these are lovely botanic gardens, and then this is a lower part of the site, and that's actually a circus fair that was put up at one stage. It was also the site of COVID testing, COVID vaccination and testing. So this site has had a number of different uses. If we look at the history of this site, we can go even further back, and we can see at one point it was actually a bottle works. It was also, there was temporary accommodation there that was probably asbestos filled. So there's quite a long history and legacy of industrial contamination. So what we are doing on this site, and this is a PhD student who's working on this, and this is work starting that I hope will be presented in many IAMG conferences in the future. But what the PhD student is doing is using a compositional approach to look at the samples taken from this site. We've got the geochemistry of these samples. We know it's actually got very elevated lead in particular, and arsenic. And what we want to do then is to compare it with this very high resolution geochemical soil sample survey that we have from Northern Ireland called the TELUS sample, the TELUS data set. And I'm very pleased that Mark Cooper, our colleague from Geological Survey Northern Ireland, is in the conference with us this week. So what we want to test is whether we can see a signature, again, these are compositional data, geochemistry data, whether we can see a signature between the industrial legacy and the geogenic, the natural weathering of the soils underneath. And this is a Triassic sandstone. So this is work in progress. And I'm going to move on to the next project where I want to show a little bit more of the background and the analysis that we've already been able to undertake. So this relates to another health and the environment project. This is a UK-funded project, and it's called SPACE. And SPACE stands for Supportive Environment for Physical and Social Activity, Healthy Ageing and Cognitive Health, which comes to space. And again, this is one of a few projects that's been funded underneath this Strategy Challenge Fund. And what we're really interested, our part in this project, is looking at the exposure analysis. So how does our local environment and any pollutants there actually contribute to our cognitive health outcomes? So we are all aging, and we hope to be around. We hope to attend many, many more IAMG conferences. So we are living longer. In fact, there's now in Northern Ireland, and Northern Ireland is not alone in this, globally, the population is getting older. There are more older people than there are younger people coming through. So that's great. That sounds good for us, for the older generation. I include myself in that. But actually it puts an increasing burden on healthcare, which we're all experiencing. And why do some people have certain illnesses, chronic diseases, and others don't if they live in the same environment? And again, in this particular case, we're thinking about cognitive health. So aging well. So our actual physical cognitive well-being. And why are some people affected with things like dementia, Alzheimer's, and others, if there's no other genetic parameters, why are others not? So what we're doing is bringing together, collating lots of different data sets, environmental data sets, with an ageing cohort of over 8,000 people in Northern Ireland, 55 and over, who have given their consent to answer a number of different questions over a period of time, and also to give some health parameters, including bloods, so we can actually start to look at their genetic markers. So this is very much work in progress, but I want to talk and show the approach that we will use and the precursor to this and why this project has developed. So bringing together all of these different data sets, whether they are socio-economic in terms of deprivation. So on the top right of this slide, these are our deprivation indices. So from a measure of income, health, employment, education levels. So a whole number of different socio-economic deprivation indices that, again, a number of different countries have. Bringing in our environmental data, and again, mentioning the TELUS project has a specific urban data sets as well for our key capital cities. And in this case, we're using a chronic kidney disease. So we're going to use this disease as a measure of aging. So as we're getting older, the number of people with chronic kidney disease is increasing. And the UK Renal Registry records the number of individuals before they start any treatment, so before their bloods are affected by dialysis or anything else. So we have been using these data to combine with the environmental data, to combine with the socioeconomic data, and to then test some spatial analysis approaches. So I should mention, chronic kidney disease, it's a collective term, and it is a progressive renal failure as we get older. It is increasing because we're all getting older, as I mentioned, and there's more of us getting older, but it's also increasing with obesity and diabetes. So there's a number of underlying reasons for it. But we know in looking at our environment then, we have the TELUS project. So again, like a number of other global geochemical surveys, we have a good environmental soil data and also stream data, I would say. But we also know there's an industrial legacy in a lot of our cities, and Belfast is no exception. You saw it in terms of the Upsurge project, high levels of lead, arsenic. In Northern Ireland, we have a legacy of shipbuilding. And we heard that Trondheim is also a legacy of shipbuilding. We also have one of the few cities to actually have a local airport. So again, we have legacy industrial pollution, but we also have modern pollution. And if you look at this map, this is the growth of Belfast, centrally growing outwards. And again, these different levels, areas can be dated, and then we can attribute some of these industrial elements to different, say, industrial processes, shipbuilding, smelting. So we know we have anthropogenic sources of pollution as well. So that is our geogenic and our anthropogenic soil pollutants. But the other thing, as I mentioned in Upsurge, we're thinking about pollution. And again, in the space project, we're also thinking about pollution. So we know already from our health practitioners that these small particles, ultrafine particles, including lead, including molybdenum, including antimony, can actually get into our bloodstream, and then they can get to our different organs, whether it's the kidneys or whether it's a brain for cognitive health. The soils do show evidence of air deposition, air pollution as well, and also our modern pollutants. And one of the modern pollutants that we're finding is increased levels of molybdenum. Now, we do have geogenic, we have natural molybdenum we know in some of the soils, but the world's production of molybdenum has just increased exponentially, and that's due to brake pads. And unfortunately, electric cars are actually heavier, and so we tend to put our foot on brakes even heavier. So brake pads are a source of pollutants in our atmosphere that are accessible to us, and the soils also can show evidence of this pollutants. So we know that there are available toxins that our soils show, and there's also available toxins in the air. So if we use this chronic kidney disease data set, and this is the data set for Belfast, so this is the urban area, Greater Belfast area. The UK Renal Registry gave us data, so age standardised rates for the less than 16 or the greater than 16 dose, so no less than 16. Greater than 16 is the whole data set, and then broken down into a number of age groups, 16 to 39, 40 to 65, and the plus 65s. And then this unknown etiology, and this is the UK Renal Registry and practitioners recording unknown causes. So everything else, the genetics and all of those have been taken into account, and these are where the practitioners are saying, we do not know the causes why this person has got kidney disease and somebody else hasn't. And you can see that it is spatially variable across Belfast. And we are actually incredibly high. We have more than 12 times higher than would be expected for our average population in Northern Ireland. We also, as a population, have an issue with chronic kidney disease. And again, Belfast is not alone in this. So in these maps, basically below 1 would be lower than expected for our population. And there are some administrative centres called super output areas that are lower, and some are higher, and some are much higher. So again, how do we analyse and bring together all of these different data sets? So we have our health data set, in this case, the chronic kidney disease. We have our environmental data sets. In this case, we're looking particularly initially at the soil geochemistry, which we know are compositional. So we need to use a compositional approach to open up some of these closed data sets, and then we can carry out any other type of regression analysis following that. So in this particular case, we're using a compositional balance approach. Now, there are a number of different compositional balances approaches, and others will be presented later on in this conference. And they all have value, merits, positives and negatives. And if I have time, I'm going to show a comparison of some of them at the end of the presentation. In this case, we're using what's this cell-bal algorithm, which uses one compositional balance approach. So this started in the bionome field, not in geoscience at all, but it can be a helpful tool in what we want to use this algorithm to test what are the components of the multiple deprivation indices, these multiple deprivation measures, and also the geochemical, potentially toxic elements whose relative abundances are associated with the elevated incidence of chronic kidney disease and also chronic kidney disease of unknown causes or etiology. The cell-bal method then uses this n-fold cross-validation procedure, and it identifies the best balance. The global balance is the one that comes up most of the time with in most of the cases, but we also can get a number of different balances, and the frequency of those then is shown in this graph to the side. And then we can use these balances for any further regression. So the case that is shown on the slide is for chronic kidney disease of unknown etiology, so the ones that we might think are more identified with the environment. It's for the super output areas, which are 92 in total for the Greater Belfast area. In this case, you can see that the global balance, the one that's identified as coming up most, is between molybdenum and arsenic. And then we can see that nickel comes up. Again, it comes up with chromium, and it also comes up with cobalt. So we can start to see some of these elements are identified more clearly than others. And I should say that in the CellBal algorithm, it also uses this mean squared error to determine how many balances. So there could be more than two. It doesn't have to be a two-balance approach. So that's interesting. So we have environmental toxins that are being identified through this compositional balance approach. And interestingly, some of the elements are coming up. We know they are potentially toxic elements. And we found in this particular case for the chronic kidney disease of unknown etiology, the balances of arsenic and molybdenum. So if we think about what we mentioned before and the brake pads, so yes, we have geogenic, but we know that the soils are also evidence of air pollution. And look at some of these super output areas with the highest amounts and overlay them with the transport networks, then we actually start to see, well, is there association between the traffic as well as air pollution, but air pollution affected, contaminated by our traffic? And again, we know, again, from the literature that arsenic and molybdenum have been associated with this atmospheric pollution and traffic pollution in particular. And brake wear emissions are sources of molybdenum and antimony. So can we take this further then in our compositional approach? So if in this one we've then taken our data, our economic, socioeconomic data, the multiple deprivation measures, we've taken our environmental, potentially toxic elements, and combined them with pollution data. So we have pollution data for benzene, carbon monoxide, nitrogen oxide, sulfur dioxide, and then the particulate matters of PM10 and PM2.5. Again, we're using this forward selection method of the CellBal algorithm to investigate. So these are some of our results for chronic kidney disease of all the chronic kidney disease cases above 16 years, and then chronic kidney disease of unknown etiology again. And you can see, again, we do have the potentially toxic elements, molybdenum, some of our key ones coming up again. But I want to, I suppose, highlight the air pollutants in particular, the sulfur dioxide, the carbon monoxide coming up, both with chronic kidney disease of all of the cases, and then also the PM2.5 and carbon monoxide coming up with chronic kidney disease of unknown etiology. This is the first time for chronic kidney disease that this sort of data have been presented and analysed. So it really is important findings. As I say, it led on to this large UK-funded project. So by using this compositional balance approach, we've been able to identify these different types of balances and associate them, not just with the multiple deprivation indices, but also then with the chronic kidney disease data. So the findings for this then, for chronic kidney disease of all ages, we're finding, again, molybdenum, zinc coming up, statistically significant, and also the multiple deprivation domains of employment, income and health. But in the air pollutants, I suppose it's really interesting to find that sulfur dioxide, carbon monoxide is coming up. And again, that's carbon monoxide coming up for both chronic kidney disease for all cases and for the unknown etiology. And PM2.5. Some work has obviously been done, and PM2.5 has been highlighted in air pollution data before, but not usually for lung cancer, but not for kidney disease. If these elements can get into our blood and get to our kidneys, they can also get to our brains and other organs. So let me move on from that. So one of the last things that we wanted to test is, are we being affected by the order in which we sort of add our elemental elements into the analysis? Because we need to know that if we're presenting these to health practitioners, if they're impacting on policy, which I hope they will do. So it's not just about having 20 miles an hour zones, it's about gently braking before you get to them, or else we're actually increasing the danger for children and our ageing population. So this study, which is the last case study, We used, again, chronic kidney disease, but for the whole of Northern Ireland. This is the Northern Ireland, and this is the Republic of Ireland, Donegal, and then and you can see where we are in relation to the UK and Ireland. So we're using all of the data set, but this time it's stream water data. And our chronic kidney disease of unknown etiology. And again, you can see a very clear spatial distribution for our highest cases of unknown etiology. And they do have an interesting association with these paleogene basalts, the Giant's Causeways up here. So that's an interesting association. And you might say, but everybody uses public water. Well, actually, we do know there's also private water use in this area as well. So again, we're using the super output areas for the whole of Northern Ireland, the chronic kidney disease of unknown etiology, just in this case. And we're going to focus on the basalt bedrock because, again, there is that identifiable visual spatial representation. So we're going to compare the CellBal algorithm with a couple of other balance approaches, not by all means all balance approaches. So interestingly, using CellBal, we get some interesting findings, and actually, the highest global balance that is coming up, aluminium, iron, are coming up clearly as being the most important elements to associate with chronic kidney disease of unknown etiology and to identify, so basically as a signature almost for this. And we do know that there are relative amounts of aluminium and iron in these paleogene basalts in the stream waters, and they're affected by the bedrock, by superficial deposits, possibly peat, by the dissolved carbon and the pH of that. So we know that there are controls on this, but it's very clearly coming up as a factor in this. But let's compare it with a couple of other balance approaches. So two other balance approaches, there are others, but two other balance approaches in compositional data analysis is the sequential binary partition, the SBP, and also just using an ILR balanced approach. So these both can be used in the R package composition. So we tested, first of all, the impact using a completely data-driven. So we know nothing, we don't know anything, we have no underlying presumptions. Let's just put all the data in and as the order that we get them. And there are clear differences between the sequential binary partition approach and just the ILR approach. But then we do know about potentially toxic elements. So let's refine our approach. Let's use a knowledge-based approach. And in this case, we're using what we've learned from CellBal to inform these other balance approaches. So if we do use this knowledge-driven approach and then try reordering the data, then actually what we find are slightly different results. Now, aluminium and iron are still coming out as very dominant, but in these approaches, they're also connected with many other elements in the balances. So, thank you. So, two things really. I suppose using a balance approach like CellBal, it identifies that we can actually work with a number of refined elements or balances of elements. And also, the CellBal algorithm, regardless of how many times we did it and reordering of elements, still gave very consistent and robust findings in our approach. Whereas when we use the sequential binary partition approach and just the ILR balanced approach, then it did matter. They were nuanced differences, but it does matter which order you put the data in. So what are our conclusions then in this case? Well, sometimes a data-driven approach, where we just put everything in and see what comes out, can be helpful as an initial exploratory data approach. But actually be aware that reordering the elements could have an impact. A knowledge-driven approach is certainly preferred. And as a geologist, I would always say that bring the geologist in, work with them, get them to guide you, and you'll get much more interpretable results as a result of that. but also be careful about the ordering and some of the balance approaches that you can be used. And certainly in our case, we found this CELBAL forward regression approach very helpful and robust in our case. And then what are the implications for health? Well, it does show again, geology is really important. Geology, bedrock geology, superficial deposits, but they also need to be combined with our information on air pollution, traffic. They can be show us a legacy of deposition, but they also can indicate some of these exposure pathways. And in this case, it was a waterborne exposure pathway. So I just want to close up by thanking obviously all of our sponsors, and I'm so pleased to have our colleague from Geological Survey Northern Ireland here with us. But also, as you know, any project has a huge team, and the SPACE team is no different, and there's a number of PhD students and postdocs working on spatial data analysis approaches. And also in UpSurge, we have a number of different colleagues and postdocs and PhD students working on this. So thank you very much for listening. There are a number of different publications associated with the work that I've shown and also arising from this work. So thank you very much.
Thank you, Jennifer, for that excellent talk. Any questions? Should we do the line thing, or will we just? Yeah, exactly. Mute. Yeah.
Did you want to ask a question?
No.
All right, Professor McKinley, thank you very much. Amazing talk. Great way to kick this off today. You got me really kind of excited thinking about geoforensics. And then what I realized was that the way we teach and educate and formulate a lot of our geology is around kind of prospecting, land use. It's such a different application. And so I started thinking, do we need to change the way we teach geology, the way we handle our data to be ready for that application?
So in forensic geology, I think it's an exciting area that students really get interested in. We teach it in Queen's University. We have a module in it, and it often leads to students taking it on. I agree with you that I think we need to expand students' outlook for how they can use geology, for why geology is so important. And what students would often say, what do I need to study to get into forensic geology or forensics? And we would always say, become an expert in your discipline, whether that's geology or chemistry or mathematics or statistics. Become an expert in that, and then that can be applied. So yes, we need to expand not just in forensic geology, but in all of the different areas that geology is important for the Sustainable Development Goals, that geology has a place to play. And I would say mathematical geoscience has a major place to play in that. But yeah, no, thank you for your question, Michael, and it's definitely Jenny.
Okay, another question? No? Looking into the crystal ball, what are the other applications that you have not presented here?
That I have worked in?
Well, perhaps not that you already have worked in, but do you see any further applications? I mean, you talked about environmental forensics. What are the other forensics?
Well, humanitarian. There was a lot of work done in, I suppose, in large scale, whether they're climate, and this is where I think, yes, there's a sort of a whole area, unfortunately, with climate change, extreme, sort of more higher frequency of magnitude, high magnitude events, and that will cause implications for slope instability, for, unfortunately, inundation, whether it's flooding or something, and then the repercussions of that will be land covered with soil, with water, with sediments. So understanding, although it's moved, the material has been moved, understanding where that material came from, what it's composed of, how easy it would be to dig, how likely it is for somebody to be able to remain alive for a certain period of time. That is probably with climate change, that's one of the areas. I would also say in health, the climate change implications for health is an area where geoscience, mathematical geoscience, it should be involved because, again, it links back to, we have people here studying climate, weather patterns, but it's also then linked to our environment, the holistic environment, whether it's geogenic, anthropogenic, air pollution, all links through to our mathematical geoscience techniques. So those are just two areas, but there are many more. I'm
just wondering if geoscientific forensic is what we do.
Yeah, exactly.
Luis?
Hello. Very, very nice presentation. I just was wondering, is this forensic also implying timing, temporal? I mean, can you predict, forecasts, for example, pollutions or over time based on data, historical data and forecast?
I think that's an interesting one. I mean, timing, temporal, spatial temporal, again, is something that mathematical geoscience and colleagues have been working on for many, many years. In terms of the air pollution, certainly for the Healthy Aging project, we are looking at the past, so we're looking at this cohort over the period of when they started being part of the cohort to now. So it's spanning over 20 years for some of our cohort members. We can look at the air quality and the different pollutants that have been associated with that over that period of time, and then start to look at temporal, spatial and temporal patterns. So yeah, absolutely. And then from that, you can start to predict how that's going to impact on cognitive health for our aging population. Hope that answers your question.
Questions? On your environmental forensic slide, you showed the sampling pattern of what I thought was the where you have sampled this part.
Yeah.
It looked very systematic. Any reason why? I mean, this is a detailed question. But it just puzzled me. Why did you do this very systematic? It looked very systematic sampling pattern.
Yeah. And it's really interesting question, and actually it's probably a whole area. There's a sort of a chapter on it, and I should have mentioned the Forensic Geoscience book. There's a whole chapter on sampling strategies. In this particular one, you were working with the City Council, and they're paying for that study, and they have their own regulations on how you do site assessments, and that's what that was listed as. For geostatistics, for a number of different spatial analysis approaches, people would use much smaller, so that you get that short scale variability, if say for variogram, as well as then more distant. In forensics, you don't always get the liberty of doing a nice spatial scale-based approach or irregular sampling grid. There are specific areas in a site or in a scene that you would sample, entry, exit points, obviously body deposition or some sort of the criminal site. We try and do as much of a spatial sampling scheme as we can. There's a cost involved. Sometimes it's a the crime scene officer who's collecting the samples. We don't always have control over how they're collected. We have moved very much away from 1, 2, 3, possibly if you're lucky, samples to a sampling scheme. And that has been educating our site scene investigators that that's required. If they want to know how spatially variable that scene is, they cannot present three samples to us. So that has been work in progress, but we've been very successful in doing that, and I think now that would be standard procedure. But there is a cost that comes with that.
Always. Okay, suddenly now 4 questions. I'm not sure who was first.
Just a short question. You mentioned that you compared the different balance approaches. Did you try the principal balance approach?
No, and there's
I think that would be interesting because it is compared to the principal components, or it is an attempt to approach principal components, and it might give you the balance that best explains the spread in the data.
Yeah, no, absolutely, and I'd like to, and I know Carol is probably here with the pivot balances somewhere as well, but I absolutely, and I think there's lots of work that can be done in this space, so yeah, like to work with you.
Yeah, thank you. Well, wonderful talk. I think it has really triggered a lot of interesting thoughts from my point of view. My name is Pedro. I work for the Norwegian Geological Survey, by the way. So I have a couple of questions for you. One is, how often geoforensics is used to solve cases? Because, as you said, ChemScan is, it's quite an expensive technique. So one would expect that, they have to be quite high-profile cases or not. So that was one question. The other question is a bit more technical, and you actually mentioned it, but I was just curious. You mentioned that, there are difficulties when it comes to use principal component analysis in this ChemScan data because you have 7 samples, but you have many variables. So I was just wondering how you deal with that problem because you show a principal component analysis or their graph, and you mentioned Eric Grunsky, which, by the way, has worked the Geological Survey of Canada for a number of years. He worked a lot, and I worked there as well. So he is kind of like a known person. Well, I don't know him personally, but he's a well-known person in Canada. So those 2 questions, how often it's used the geoforensics, and then just a summary or briefly how you deal with that problem with the amount of variables versus the amount of data.
So in the answer to your first question, in forensic geology, I suppose, again, it's working with the police service, and when they realise that there is this expertise available to them, then they ask. So it's always as an invitation. So as the initiative in forensic geology has become more recognised, then law enforcement agencies globally have asked us to come. Sometimes it's to run a workshop with the local police service so that we can then train them, make them more aware, make them aware of the resources or the expertise, certainly within their local area. So there have been times when, say, UK forensic geoscientists have helped a case in Australia, but sometimes it's actually coming in as a expert to analyse the local, what's been done. So it's almost like brought in by the defence, almost sometimes to compare. Generally, forensic geoscientists are academics or in different institutions and not necessarily paid for what they do, but our payment is publications, so being able to actually publish our work. So it's the analysis that would actually cost rather than the forensic geosciences' time. That's very attractive to police services. Sometimes actually there's too many cases that you just cannot. And my colleague that I mentioned, Alistair Ruffell, has been very, very open with his time and will go out, weekends, wherever, when needed, because obviously it can result in a publication. It's not just the high publicised crimes, yes, do attract. This was not a highly publicised crime. This was a young woman that had no family, and it was really good to be able to call in and to help in that investigation. In terms of the compositional and the, very limited number of samples and much higher components, the scripts in R that are in compositional are not designed for that. So yes, it is bending the rules in R to get it to actually analyse, and that's more the issue. So I think forensic geoscience is not the only area where we've very limited samples. So I think we need to work with our colleagues in developing the scripts so that we can override them sometimes, because that's what we did. And we had to override our script and say, ignore certain conditions, sort of just do. So it's not the principal component analysis that's the issue in that. It was the... It was more our scripts for compositional. And obviously zeros is another area, which is, again, sometimes you do find that you have zeros, so you have to ignore them. And that may or may not be the correct way to do it. But it is obviously an issue in compositional.
Good. Quick answer, and then coffee.
Jean-François Lecomte, data engineer and scientist at AFPN in France. Just a quick question. I find the presentation amazing, and I just want, in the space project, I think I didn't understand. I think there is a difficulty to go from correlation to predictive interpretation. And do you think there is something to do in that? How can we be predictive in such a project?
Yeah, no, thank you. And I think that's a key thing that as geoscientists or mathematical geosciences, we need to work with the practitioners. In the space project, the work that we did on chronic kidney disease, and I should have mentioned my colleagues, so Damien Fogarty is a renal expert. So he was the one that asked us to look into this. Uta Müller was one of my key colleagues in the mathematical geoscience, and I should have mentioned them. In the space project, we're working with the Centre for Public Health. So we're working with experts in, basically Alzheimer's and dementia. So again, they are key partners. One of the areas and work packages that I'm quite excited to work with is our colleagues in epigenetics. So they've already looked at the genetic markers and have their analysis for certain markers. So we all start with genetic markers, and then there's basically a decay function as we go through life. But some people with the same genetic markers still get different are affected by different chronic diseases, and especially in terms of cognitive development. So they're looking at those particular epigenetic markers and indices, and the next stage is that we're going to use some of our compositional approaches and the pollution data and soil data, and to then to do an analysis. You're right, it is an association, but then it allows them to look further at their epigenetic data to see, can these really fine particles that have entered these people's bloodstreams, so if we find those in the bloods, then can they get a closer indication of whether that might have been the impact that has changed their epigenetic decay function faster, say, than somebody else? Is it ever 100%? It's a bit like forensics. I don't think we'll ever be able to say 100%, but if we can guide policy, or we can guide a practitioner to actually look out for certain markers in the blood that are associated with elemental data in the bloods, or whether it's geogenic or anthropogenic, then that will help be able to focus that person's treatment, or being able to say, well, certain people live, because this is what it's about. It's about what are you affected by on your daily walk, on your daily commute. What are the impacts? So if we can then address that, then we can start to reduce the risk for those epigenetic indices having a faster decay process or not. So yeah, never 100%, but it's working with practitioners, and they know what they're looking for. They understand the mechanisms of these elements getting into the blood, but they need the evidence base from us to say, yes, these are the key toxins that you need to look for in the epigenetic markers, and likewise.
Okay, thank you. I think, Louise, you had a hand up, but we'll take it over coffee break, please. Thank you, Jennifer, for an excellent talk, and I think a very nice discussion. Thank you for that.